been a little wild this morning. All right, good morning, lads and ladies. Welcome back to Calc 1. Today will be our third and final day focused on U substitution. We're going to look at some of the more challenging problems that can come up. And we're also going to introduce section 6.1. Sorry, I just got to look at my hair this morning and realized it looks a little bit wilder than usual. So get that fixed. All right. So over the last couple days, we've talked about U sub. We have seen a handful of cases, some of which are nice and simple, some of which are a little bit more challenging. Today, we're going to build on that. There's not a whole lot more that can happen that you haven't seen, but sometimes the mechanism to get in there and replace those last little bits can be kind of tricky. So I just want to show you one or two problems of a slightly higher caliber. This, of course, is MAC2311, section 002. It's a lecture, and the date is the 9th of April, 2021. Today we're going to do some more U sub. No problem. And we're also going to introduce section 6.1, which is the last section in this class, which is on areas between curves. A little announcement. I'm gonna have to abandon this pen. Little announcement. The student opinion surveys are available in East Santa Fe. They've been open for a minute, but these are available. So I would love it if you would take the time to complete them. They really don't take that long. If you complete the opinion survey for this class, nothing magical or wonderful happens, but it is really useful feedback. It's useful to me to help me improve the course moving forwards, and it's useful to my superiors to help decide if I get things like tenure, that sort of stuff. It's not the end all be all, and there's lots of other ways that you can give me feedback or give the department feedback on the course, that sort of thing. But this is one of the main ways, and the response rates on these are usually very, very low because there's not much incentive. I get that, but it only takes a few minutes. You can go in there and let us know what you think about the course, what you'd like to see changed, what you like to see continuing the way it is. All of that. So any information that you wanted to provide that you thought would be helpful, constructive feedback, really, really appreciated. Takes about 5-6 minutes. It's not that bad. I mean, if you just Christmas tree and don't type any comments, you can get it done in like 2 minutes. If you want to type a bunch of comments, it might take 10 minutes. It's not a long time. And it really does help me improve the course. So anything that you want to say, you can say there. It's totally anonymous. And I would really appreciate it. All right. More U sub. I have a few particular problems in mind, but I think it would be best if we kind of built up to that. So let me poke around in section 5.5 and see if there's something in here that looks fun. Something a little bit challenging. What do we have? Could do that. That's super duper straightforward though. These are all pretty straightforward. They don't, so this section doesn't have a whole lot of like truly challenging problems. But we can look at one or two here. I think we did something very much like this in class the other day. I would like to do something perhaps a little bit wilder. Let's look at number 42, the cosine of the natural log of t over t. Oh, so an example. The reason these can't get too out of hand is because, substitution is the only technique we have. And the textbook problems are all meant to be solved to completion. So really, there should be another little parenthesis set around the t in here. I'm going to go ahead and write it like that. It's the cosine of the natural log of t, all divided by t dt. This is what we want to evaluate. You've been doing a fair amount of these lately, so who can help me out here? What would be a good move to substitute for?
LNT.
Yeah, very good. Remember, we often want to sub for the inner function. Wherever we see an outer and an inner function, we often want to sub for the inner function. We also notice that there's this t downstairs here, right? Knowing that the derivative of the natural log of t would be 1 over t. We can kind of see how this might be nice. So I make the move u equals ln t. Du then would be what?
1 over x dt.
So it 1 over t dt.
1 over t.
Variable here is t, but yeah, we got the right idea. 1 over t dt. There are no bounds here, so we don't need to worry about changing any bounds. And then if I start plugging things in, the cosine of the ln of t would be the cosine of u. I'll just leave this guy down here. Maybe even I'll leave the dt here in this step. All right, what would be my next move?
Cancel out the t's.
Yeah, I need to do something with this t here. And the main thing is replacing this dt by its equivalent du expression, right? So there's a handful of ways to do that. I think the way that most people are comfiest with is coming back here and solving this for dt. So if I solve this expression for dt, I do that by multiplying both sides by t. I get t du is equal to dt. So everywhere there's a dt here, I can swap in t times du, and then my integral will become integral of cos u over t times t du. And like Mackenzie said, these t's are going to cancel. So we end up with the integral of cos u du. All right, how do we proceed from here? So at this stage, substitution is done. All right, this is the step where we finished the substitution. We've gotten rid of all of the old variable stuff. So now we're free to start thinking about antiderivatives. We don't want to plug anything in at this stage. It's true that because this is an indefinite integral, at the very end, we will plug in u equals the natural log of t. But only at the very, very end, only after we've gotten our antiderivative and written plus c. So what do I do at this step now? I've done my substitution. I've transformed the integral from a t and dt integral into a u and du integral. So what should I do now, right at this stage?
Find the antiderivative.
Yeah, perfect. This is our step where we cook up our antiderivative. All right, I've taken it from an integral I don't know how to do in terms of the variable t into an integral that I do know how to do in terms of the variable u. An antiderivative for the cosine of u is the sine of u. All right, because the derivative of sine u is cos u. And now we can plug back in. So u is the natural log of t. That means this is the sine of the natural log of t plus c. All right. This is a great problem. Nothing mortally challenging here. The term from the differential canceled with the extra copy of the old variable that was left over, right? At this stage, we should be concerned. We should be concerned because there's still this t down here. But as always, after plugging in the thing that you're substituting for, right? We chose to substitute for ln t, so we plug that in for u. The first thing you do after that is plug in for your differential. So we solve our differential for dt. And then we plug that in. So dt was equal to t times du. And when we plug that in, we see that those cancel. I want you to take a second. This is kind of a quintessential problem. It really does have all the pieces that you can expect from a classic u sub in an indefinite integral. So are there any questions at all on what we did here, why, notation, anything? Okay. I'd like to ask you now, what do you think we can do if I take this same integral and I get rid of the t downstairs?
Like sub u for t or t for u.
Well, let's take a look at it. Let's see how that looks. So let's execute the substitution in integral cos of the natural log of t. And I'm actually going to do one further. I'm going to make this a definite integral. I'm going to say this integral goes from 1 to e. I'll tell you right now, we're not going to finish this problem. All right? We just want to execute the substitution. The reason we're not going to be able to finish this problem, the reason we can't, I'm limited in the challenging examples I can show you, is because most of these lead to integrals that require something called integration by parts, which we don't know yet. I'll be teaching you that in the first few weeks of Calc 2, if you choose to take that. But here I'm just interested in the substitution. So I want to transform this integral into a different integral. And I'll tell you the substitution I want to make. So the u equals t substitution, I do see people do that occasionally. It doesn't change anything, right? If you make the substitution like u equals x or u equals t, all you're going to end up doing, you're going to end up with the exact same integral, just with t's replaced by u's. It won't actually get rid of or add or change anything. The substitution, the natural one here, is the same thing. Same thing we did in the last guy. Because I've got like an outer and an inner function, kind of the natural thing to do is to substitute u equals the natural log of t. Which means du is still 1 over t dt. And I would change my bounds when x is equal to 1. What is u going to be equal to? I'm making this substitution, u equals natural log of t. What does the lower bound of 1 turn into?
0?
Yeah, good. It would be the natural log of 1. Remember, you just take the old lower bound and you plug it in for the old variable. Oh, sorry, this is a t. I'm sorry, not x, when t is equal to 1. Yeah, u would be the natural log of 1, which is 0. And when t is equal to e, u would be the natural log of e, which is what?
One.
Yeah, very good. Natural log of e is 1. Okay. So my new integral would be an integral from 0 to 1 of the cosine of u. Oh, but I still have this dt here. So what should I do now?
Substitute in
So-
D.
So I heard a few ideas, right? It's got to have something to do with this, yeah? I need to get rid of all the t stuff. I still have this dt. So what was the recommendation?
Sub dt for d u t.
Yeah, I can solve this for dt. This means t times du is equal to dt, just like it was in the last one. Okay, that gives me integral 0 to 1 cos of u times t du. Well, this is bad also, right? Because I don't have that t downstairs. There's nothing to cancel with this t. So far we've done the same steps we did in the last guy. But I'm left with an issue, and this is an issue that we saw on Wednesday also. If after doing all of the natural things, all right, you replace the piece by u, you change your bounds, you plug in for the differential, but uh-oh, not everything cancels. You've got a little bit of this old variable left over. How do we handle that?
Rewrite t in terms of u.
Very good, all right? So I need to rewrite t here in terms of u. What's the tool that allows me to do that?
Your u equal to ln t.
Very good. Everybody hear what Adrian said? So we use our substitution. Our substitution is u equals ln t to rewrite this piece t in terms of the variable u. In other words, I need to solve this equation, u equals ln t, for t. How do I solve this for t?
Would it be e raised to u is equal to t?
Yeah, very good. Remember, the way you solve logarithmic equations is something I'm teaching my college algebra students right now. You exponentiate on both sides, meaning you put both sides in the exponent of e. And then on the right-hand side, e raised to the power of ln t is just t. So u equals the natural log of t is equivalent to saying t equals e to the u. All right, remember, natural log is the inverse of the exponential. So this becomes integral 0 to 1 cos u times e to the u du. And now the substitution is done. And I'll tell you, this exact problem has shown up on my exam 1 in Calc 2. All right, saying just make this substitution, u equals ln t, go in this. Don't solve the problem, just pick out which integral you get when you do that, or some variation on this. Real common stuff, and it's something you need to make sure you're comfy with. Now, how do you solve this integral here? It's a little bit of a doozy. It requires, like I said, integration by parts, which is not something we know. It's not something we're going to learn in this class. It's something that we'll have to wait until Calc 2. That's why it's not something I could really ask you at this level to evaluate. But getting from getting from this step to this step is something you should be comfy with. And this happens not infrequently, right? Where you'll have some number of your old variables left over after you do all of the obvious stuff. The reason I wanted to show you this particular problem is because that extra t here, this didn't come from something that was like floating around in the original. It actually came from the differential. All right, the t in the t du there is the differential. but it can still cause that same problem that the x in front of the square root caused in our second problem on Wednesday. That it, not everything goes away after you do all of the obvious stuff. And even in that instance, no matter where it's coming from, if you have any of your old variables floating around after you do all of the natural stuff, you go back to your substitution, solve for the original variable, and that will let you replace whatever expression you have with a new variable expression. Questions on this? Right. For the record, integrals like this, they have a name. They're called damped harmonic oscillators, and they're very important. Things like cos u e to the u, like sine or cosine times an exponential, these show up a lot in differential equations. Solutions to constant coefficient linear differential equations pretty much always look like this. And they can describe physical systems. Things like this are a big deal in physics, differential equations. And so you'll be seeing integrals like this quite a bit in your future if you're going to go down any of those routes. All right, we can take one or two more problems here, but I think we're getting close to being done with U sub. Is there anything that you guys want to see? Anything from the homework that you guys are struggling with? Any particular problems that you would like to take a look at? I wouldn't mind looking at a little bit more trig stuff. Tan squared, secant squared, cube, secant squared, cos cube sine. Yeah, let's look at one or two more things here from trig land. And then we'll talk a little bit about 6.1. I like these trig integrals because it's not always immediately obvious what you should substitute for. It's not super simple in the inner-outer sense. Ideas?
I believe you would do tan theta.
Yeah, very good. Very good. Adrian, can you tell us, I don't mean to put you on the spot, but can you tell us why tan theta? What's so intriguing about the substitution tangent theta here? U equals tan theta.
Because when you take the derivative of the tangent, you get secant squared. And so after you take the derivative of u, you'll get secant squared d theta, and then you can replace that with du.
Perfect.
So you have u cubed du.
Yeah, this is the nice move here, right? So I have a power of tangent times secant squared. I know that secant squared is the derivative of tangent. So if I substitute u equals tan theta, du would be secant squared theta d theta. Now lately when I've been solving these problems, I've been saying, kind of come in here and solve for the d theta or the dx. But another way of looking at that again is to say, oh, look at this. All right. So that piece right there is straight up just is du. So tan cubed theta, that's u cubed, right? Because this is all right like this. This is tangent of theta all cubed times secant squared theta d theta. So this piece is going to be my du, and this is just going to be u cubed. So these trig integrals, if you're a little bit clever about it, you just have to kind of think ahead a half step or one step, really, you know, like in chess. If I do this, then what will happen? If you think ahead just that one step, then you can do these very, very quickly. They're not hard. Of course, the integral of u cubed is 1/4 u to the 4 plus c. You could write it as u to the 4 over 4 if you want. And that would be 1/4 tan to the 4th theta plus c. Sine cosine integrals can go like this also. Let me try. What if I want to integrate sine 2021 theta cos theta d theta? So the power of sine there is 2021. Following the same sort of logic, I know that the derivative of sine theta is cos theta. And of course, sine to the 2021 like that, that's just a shorthand for sine of theta all to the 2021. So if I make the substitution u equals sine theta, then du is cos theta d theta. And this will become the integral of u to the 2021 du. There are variations on these problems. So this would be u to the 2022 over 2022 plus a constant. And then at the very end, having already done our antiderivative, now at the very end, we plug back in. Some of the variations on this theme can be a little bit challenging. And I'll give you a small taste of that. And then we'll go talk about 6.1 real quick. Okay. I want you to apply that sort of chess logic here. And you need to be mindful of some trig identities for this one. Oftentimes, when it comes to integrals involving trig functions, identities are the key. This is very similar to the problem we just looked at. We had some power of sine times some power of cosine. But the thing that made that last problem work out so nicely is that the power of cosine was 1. So when I substituted u equals sine theta, du ate up all of the cosines. Here, it's not so simple. And I would like you to think for just a second while you think. I will refresh my coffee. What should I substitute for? What can I make work here and how? I'll tell you the identity that will be useful is the Pythagorean identity. Use sine squared theta plus cos squared theta equals 1. All right. Any thoughts what we could do here?
Would you make sine squared equal to u?
So if I made u equal to sine squared, then du would be 2 sine theta times cos theta, right, by the chain rule.
Mm-hmm.
And then my differential would soak up one of the sines, one of the cosines. So I'd be left with u squared times cos theta d theta. Sorry, u squared times cos theta du, right, after we plug in our differential. So I don't think I have an easy way to get rid of the cosine if I do that.
Okay. So
There
my
are-
other guess would be a cosine squared equal to u.
I like the cosine suggestion. So if we try subbing u equals cos theta, du would be negative sine theta d theta. So if I start plugging things into my integral, I'll write it down here, integral sine cubed theta cos squared theta d theta. Cos squared is going to be u squared. So I'd have sine cubed theta times u squared. And then if I'll leave this as d theta for now. Okay. Now I can take this and solve it for d theta. I'll treat it like we were doing before. This is negative 1 over sine theta du equals d theta. And when I plug that in here, I have my sine cubed theta times u squared times negative 1 over sine theta du. So I've got my du in now. I've switched the differential from d theta to du. D theta is equal to this thing. And the sine theta here will cancel with one of the sine thetas here, right? Everything here is being multiplied. I can cancel. And that will knock this power down by 1. So that gets me to integral sine squared theta times u squared du, and I can shuffle this negative up front. It still looks like I'm in trouble, doesn't it? Because I still have this old variable stuff floating around. I still have a sine squared theta here. How can I rewrite sine squared theta in terms of u when u is cos theta?
Can't you do the antiderivative of u?
Like, remember, I can't do any antiderivative stuff until I get rid of all the old variables, right? And I still have the old variable theta here.
Well, sine
Okay.
squared theta equals negative cos squared theta.
Oh, right.
Sort of.
Yeah.
Sine squared theta isn't the same as negative cos squared theta, but there is a relationship between them. This is where this hint comes in. Sine squared theta plus cos squared theta equals 1. If you subtract cos squared from both sides, that means sine squared theta is equal to 1 minus cos squared theta. That's the magic here. So let me just plug that in and then we'll take a look at it. Integral, negative integral, 1 minus cos squared theta times u squared du. Why is this good? What is 1 minus cos squared theta? So remember, my goal is to replace this by its equivalent expression in terms of the variable u. How does
Because
this as this help me do that? Yeah.
because u squared would be cosine squared.
Excellent. If
Or
u
theta. So they're similar terms.
perfect. Yeah, if u is cos theta, then u squared is cos squared theta. This is cos squared theta, so it's the same thing as u squared. So this becomes negative integral, parentheses, 1 minus u squared times u squared du. And now you have a polynomial, right? Now the substitution is done. And this is not a difficult thing to integrate. I've got negative integral, distribute the u squared. I get u squared minus u to the 4 du. So that's going to have an antiderivative negative bracket u cubed over 3 minus u to the 5 over 5 plus c. And now at the very end, having found our antiderivative, we can plug back in u is cos theta. I'll also distribute the negatives. This is negative cos cubed theta over 3 plus cos to the 5 theta over 5 plus c. Integrals of this form, powers of sine times powers of cosine, are extremely important, really common problems. Sine and cosine form what are orthogonal functions, and integrating products of orthogonal functions, again, turns out to be a big deal in higher math. There's a whole section of the textbook dedicated to these problems, by the way, section 7.2. And they're introduced by looking at very simple examples like this, where you can get away with just a little u sub and trig identity work. But we build up from there to considerably harder ones. Okay. I think that's all I have to say on u sub, lads and ladies. You've got a nice beefy homework set to be working on, and I encourage you to take it quite seriously. Please don't plug any of that shit into those stupid online calculators. Take your time and make sure you really understand each problem, because it'll be not just a huge help here. Of course, the stuff is going to be on exam 3 and on the final, but it's also going to be a huge help when you get to Calc 2, because the whole first half of Calc 2 is integrals like these. All right. The last thing I'd like to do today is just look a little bit at some 6.1 stuff. I want to kind of gently introduce the idea of areas between curves. We'll look at the full detail stuff on Monday of next week, and then that will be your last section of the class, really. There's one or two tiny topics that I want to go into and poke around with at the very end. But we are here now. We are at section 6.1, which is the last little bit. So I'm going to wrap up this week just by giving you a taste of what we're going to do next week. I wanted to set the date for exam 3 today also, so let's go ahead and do that. I think probably the way to do this, let's see, we certainly could do it on the 16th, but I'd like to give you a full week between the last day of lecture and the day of the test. So I'm thinking the 19th is probably going to be our exam day. So let's go ahead and make that official. Okay. One last little remark, announcement.
Professor, I actually have one question
Sure.
before we move on.
Yeah.
So in the homework, there were some trig formulas we needed to know to take the to do the substitution with. Are there should we just know all the general trig functions going into the third exam and the final, or are there specific ones that we should know?
I want to make sure I understand what you're asking. So you're asking about derivatives of trig functions or identities for trig functions? What kind of things?
So identity, trig identities, knowing those identities to do some substitution.
Definitely the Pythagorean identity, which is this guy.
Okay.
I expect you guys to know that. And its other forms. So tell you what, let's do it like this here. We'll say exam 3 is 419, and then I'll give a list of some things that I require you to know for the purposes of the test. So exam 3 will be Monday, 4/19/21. That's a week from next Monday. And then things you need to know. Exam 3. You need to know the formula for Rn and Ln, right? The Riemann sums. You need to know the definition of the integral from a to b of f of x dx as the limit n goes to infinity of Rn, which is lim to infinity sigma I from 1 to n f of xi delta x with all the little bits here. Remember, delta x is always b minus a over n, and xi is a plus I delta x. You need to be comfortable with the properties of the definite integral. So those include like linearity, the fact that you can split up in the middle, the a to b, negative b to a, the even odd function stuff, all of those properties that we discussed of the definite integral. You need to know the table of antiderivatives. Table of basic antiderivatives. Plus those two that we talked about recently, the integral of tan theta and integral of secant theta. What else? I'm sure I'm going to forget something here. You need to know the kinematic stuff. E.g. displacement versus distance. And of course, U sub. So these are the main things that are going to be on exam 3, just off the top of my head. Now, when it comes to the U sub stuff, some useful trig things that you need to know, of course, you need to know the trig derivatives. And inverse trig derivatives. And of course, the associated antiderivatives. When it comes to trig identities, definitely, as always, You need to know the Pythagorean identity. And its two other reformulations, those are tan squared theta plus 1 equals secant squared theta, and 1 plus cotangent squared theta equals cosecant squared theta. Although I'm hard pressed to think of a place where you really do need those in U sub. But definitely these three trig identities, I expect you guys to remember them throughout the whole class, right? We use these pretty regularly. Although again, aside from the like problem I just showed you, I can't think of a lot of places where you would actually need them. But
Okay.
those are the major topics.
Thank you.
Yeah.
Yeah, I mean, there was a double angle trig formula we needed to know.
Oh yeah. Yeah. So that one is useful. I forgot about that being on there. Yeah, 2 sine theta cos theta. This is a useful fact. Sine 2 theta is 2 sine theta cos theta. Yeah, there is one substitution problem there where the most natural path involves this. So that is probably fair game.
Okay, thank you.
Of course. All right, with this out of the way, let's do a little gentle intro to 611. We might finish a bit early today. Maybe the more complete list. All right. So a little intro to 611. So suppose you want to find the area between the curve y equals f of x and the curve y equals g of x from x equals a to x equals b. So do color stuff. Let me see what colors I have that are working here. Blue, that works well. Is orange alive? It is. All right. Pains me to put these colors together, but we are in Gainesville, so let's do it. Let's say the blue here is f of x. And the orange here is g of x. And maybe here's a. And over here it's b. The area I'm interested in is the pencil shaded area in here. And I've drawn this with the orange function g, not necessarily being positive, because I want to emphasize that it really doesn't matter whether g is positive or negative. It doesn't matter whether both functions are positive or negative. All that really matters is their relative position. So imagine I take your favorite x value in here. Any arbitrary x value in here, and I choose to put a little rectangle or a little strip in there. Think of this as a tiny little Riemann rectangle, right? A little part of a Riemann sum. What's the height of this rectangle? So the area of the strip. I'll say the strip has thickness here, like a width. Call it dx. So the area of this little strip I'll call dA. It's a tiny little area. D you can just think of as being a short, tiny, just tiny area. So the tiny little area there is going to be the height times the width, right? The width, we said, I'm choosing that to be dx. I just think of it as a teeny tiny little width. But what's the height? If this is at some x value, we'll just call it x. Well, what's the point up here? If I'm along the blue curve, f of x at x, then this is the point x comma f of x. And down here, this point would be x comma g of x. So the height of this strip is the y value here minus the y value here. So the height is f of x minus g of x. And the width is just dx. So the total area between these two curves would be the integral from a to b of this f of x minus g of x dx. We would integrate or add up all the little areas to get the full area. Each one of those little areas is the height times the width. The height is f of x minus g of x. The width is dx. This is the way the book presents it. I don't think there's anything wrong with it. It's nice. But there's another way to present it if we assume both functions are positive. The kind of intuitive presentation that I like assuming both functions are positive. Here's f of x. Here's g of x. That's orange is dying. Here's how this was first explained to me, and then I had to accept the more general case down the road. Here's A and here's B. So the area I'm after here, the area between the blue and the orange, I'll shade in pencil again. You can think of it as the area under the orange function minus the area under the blue function. So I'll shade first the area under the blue function, and I'll shade that in blue. And then I'll shade up here the area under the orange function. And you can see that the pencil shaded area, which is what I want, the area between the two curves, is equal to all of the orange area minus all of the blue area. Intuitively, this is how I like to think of it, but it only works if the functions are positive. So the area between F and G, which is the area in pencil, is equal to the area under F which here is in orange, minus the area under G. You guys see it? The thing I want, I can calculate by taking all the area under the orange function and then subtracting out all the area under the blue function. And what we'll see is that this gives me the same thing. So what is the area under f of x from a to b? Well, that's the integral from a to b of f of x dx. And then this minus is that minus. The area under g of x from a to b is the integral from a to b of g of x dx. And if you put these two integrals together, right, they're both going from a to b. You can combine them as the integral from a to b of f of x minus g of x dx. And you get the exact same thing we got using the book's argument. So this is how you find the area between two curves in the simplest possible case, right, where the curves don't intersect and both functions are functions of x, meaning both can be written as like y equals f of x for some function. Let's do a quick example or two, and then I'll let you guys go. Again, here's how the book hooks it up, which is fine. And here's thinking kind of intuitively just about area inclusion. Let's sketch a quick graph of sine and cosine. So here's sine x from 0 to pi. And you know, it kind of continues doing this wave shape. And here's cos x. Imagine I want to find the area between sine and cosine sine x. Imagine I want to find the area between sine and cosine from x equals 0 all the way out to x equals pi. You see something interesting happens. They trade places. So the recipe that we had said, you know, to find the area between two functions, f and g, you take the upper function minus the lower function, and you integrate from a to b, right? Integral from a to b of upper f minus lower g. But here they swap places. So if we want to find the area between sine x and cos x from x equals 0 to x equals pi, I really have to consider two separate pieces. It'll be the integral of the upper minus the lower here. And then to that, I need to add the integral of the upper minus the lower here. And the upper function in the first region is cosine. The lower function in the first region is sine. The upper function in the second region is sine, and the lower function in the second region is cosine. So let me call these A1 and A2. In order to sort this out, I need to know what is the x value where these guys touch, where they trade places. So what is that? What is this x value where the graphs of sine and cosine cross over one another? for what x value between 0 and pi over 2 are sine x and cos x equal to one another?
Pi over
Pi over 4.
Pi over 4, yeah, very good, right? Think about your unit circle. Pi over 4 is where sine and cosine are equal. So A1, this first region, is going to be the integral from 0 to pi over 4 of the upper function minus the lower function. And from 0 to pi over 4, the upper function is cosine, the lower function is sine. This will be integral 0 to pi over 4 cos x minus sine x dx. And while we're here, I'll say A2, that's going to be the integral from pi over 4 to pi of the upper function minus the lower function there. Well, the upper function here is sine x. And the lower function here is cos x. So it really is that simple. You integrate upper minus lower. But you do need to be careful if your curves cross, if they trade spots. You'll need to consider those separately. All right, so let's go ahead and crunch out A1. A1 integral 0 to pi over 4 cos x minus sine x dx. What is an antiderivative for cos x minus sine x? This is a nothing integral. We know exactly how to do this. Antiderivative for cos x is
sine x.
Sine x. And then I'll have minus from the formula. What's an antiderivative for sine of x?
Negative cosine x.
Very good. So I'll have parentheses negative cos x. And this is a definite integral. We're going 0 to pi over 4. So those are the evaluation bounds here. So this is sine x plus cos x. Zero to pi over 4. When I plug in pi over 4, the sine of pi over 4 is, I'll write it, sine cos pi over 4. Subtract from that the sine of 0 plus the cos of 0. All right, what is the sine of pi over 4? Think unit circle.
Square root 3 over 2. Oh, sorry, no, square root 2 over 2.
Yeah, root 2 over 2, right? Sine and cosine are equal to each other at pi over 4. So these are both root 2 over 2. This is root 2 over 2 plus root 2 over 2 minus, what's the sine of 0?
0,
And the cosine of 0?
1.
Good. This is a 1. Want to, you could write it as 0 plus 1 to make super clear where everything's coming from. Root 2 over 2 plus root 2 over 2 is 2 root 2 over 2. It's just the square root of 2. So this is the square root of 2 minus 1. That's it. The area A2 now is the integral from pi over 4 to pi of sine x minus cos x. It's going to go very similarly. Turn the page. Are there any questions on the calculation here for A1? So for A2, we integrate pi over 4 to pi, sine x minus cos x. dx. And this is very similar. The antiderivative knowledge we need here is the same as from the previous problem. Antiderivative for sine x is negative cos x. And then there's this minus from the formula. And then an antiderivative for cos x is regular old sine x. And this gets evaluated between pi over 4 and pi. When I plug in my upper bound, I'll have negative cos of pi minus the sine of pi. And from that, we need to subtract what we get when we plug in our lower bound, which is negative cos of pi over 4 minus the sine of pi over 4. A lot of negatives here to keep straight, a lot of unit circle stuff. I want you guys to help me out. What is the cosine of pi? Forget about this negative for a minute. Just what is the cosine of pi?
-1.
-1, right? So this is negative -1 minus, what's the sine of pi?
0.
Good. And we have minus, negative. What is the cos of pi over 4?
Square root 2 over 2.
Good. And the sine of pi over 4 is also square root 2 over 2. So -1 is +1. +1 minus 0 is 1. So this is 1. Then we have minus here. And then negative root 2 over 2 minus root 2 over 2 is negative root 2. So this one comes out to 1 plus the square root of 2. So if we put these together, we'll get that total area. A1 is the square root of 2 minus 1. A2 is the square root of 2 plus 1. So the area between sine x and cos x, x equals 0 to x equals pi is A1 plus A2. A1 was the square root of 2 minus 1. Plus A2 is the square root of 2 plus 1. So you have root 2 plus root 2, and then plus 1 minus 1. That's 2 times the square root of 2. That's it. Finding areas between curves is not terribly hard. Of course, the integrals can get more challenging. The integrals here were not difficult, but the idea is that setting up these problems is not terribly hard. On Monday, we're going to learn how to kind of do these when things are rotated. If your curves are like sideways parabolas and a line or something like that, things that can be a little bit more geometrically complicated. But this fundamental idea of integrating the upper function minus the lower function is the whole picture, really. And you can think about it either the way the book does in terms of a little strip and then subtracting at the height of the strip, or you can think of it as one area minus the other area. You just have to be careful with the signs, SIGN signs. That's all I have for you guys today. Are there any burning questions before I let you go? All right, please work hard on USub. Make sure you get good at USub. That's so important. I've been doing my best to emphasize it. I hope you've really taken it to heart. You need to get good at USub. As long as you do, you'll have a breeze in the first half of Calc 2. You won't fall behind. You'll be in good shape. Also, it'll serve you very, very well on the final and on exam 3. Remember, exam 3 is going to be on the 19th. That's Monday after next. One other little thing before I let you guys go, I have jury duty. So it's the 13th, which I'm not sure if it's going to affect you guys or not. Let me take a quick look. There's the 9th, 13th, therefore Tuesday of next week. So, okay, so it's not going to cause any trouble for you guys as far as class is concerned. If the jury duty ends up going on, I may end up needing a sub for Wednesday. So there's a possibility that your class next Wednesday will be taught by somebody other than me, or I might pre-record some lectures. I'll let you know. But I just wanted to give you a heads up that there is a chance that I will not be around as much next week because I got summoned for a jury duty. That's it. I hope you guys have a lovely rest of your day. I will see you next time or in office hours.